Welcome to our NPTEL courses on advanced power electronics and control. Today we shall discuss about effect of the source inductance. That is the remaining part which we have continued to discuss in our previous class. That we shall discuss about little modern topic, that is PWM rectifier. We have learned about the full control rectifier, half control rectifier and lot of topics. So, we shall see that, but one problem is that actually the THD. So, but to reduce that THD you require a solution like actually 12 pulse, 24 pulse, even 48 pulse converter, but that require a different definite structures. So, that is not feasible for small power household application where our lot of apparatus are DC, like your mobile charger, your SMPS of the desktop or laptop, all are basically essentially AC to DC. So, we shall see that. So, this is an important topic have pop up due to the invent of the actually more and more actually DC to DC applications, that is PWM rectifier. So, we shall continue today first the remaining part of the source inductance, we shall discuss in details about the PWM rectifier. So, let us go back again. Actually in this configuration we considered, we have talked about the RC load, now we talk about the RL load, and we have some amount of the source inductance into the placed. It may be due to the leakage reactance of the transformer or any external resistance added, or even that actually that line has its own inductance. This is actually the 3 line voltages 120 degree apart balanced, and ultimately you will find that actually this is the 6 pulse load voltages, but this hash area essentially you can find that where both the diode, 3 diode is conducting. Generally what happen, one diode from the most positive phase from the forward half cycles and the most negative from the negative half cycles, lower part will conduct, but here we will find in this actually hash region 3 diodes are conducting. So, what will happen due to these conductions, you will find that they actually some point of time, let us say this area where actually phase AB actually goes to negative, you will find that there is this particular to this area. So, you do not get any voltages. Same way it will happen also when actually this conduction changes. Since there is an inductance, and also actually we will find that actually rise of the current like this. So, it will take some time, the current through the D1 was actually to rise with some value, and since before that D5 was conducting because it was the most positive phase. So, in this region D1 and D5 both will conduct for the some time, and thus actually there will be a dip in the load voltage. So, similarly when actually A goes off, so ultimately due to the negative half cycle, so then actually outgoing diode will come into the picture, B basically will pick up. So, in this region also, so ultimately D3 will come into the picture, and in this region also you will get an overlapping, and due to that there will be a little sag in the DC bus voltage, and this will be the current of the IC, and ultimately you will get basically this is the amount of the current. So, let us analyze the circuits. So, we can write phase values VA equal to when LDIdt of the source inductance plus the load voltage. Similarly, VB will be the load voltage. So, we can write actually VA minus VL equal to basically the source voltage. From there we can integrate, we can find that actually from the time that is called overlapping angle pi by 6 to mu plus pi by 6. So, this incident will occur, and so we can have to find it out what is the amount of the ID, the circulating current due to that time. So, we will find that this by integrations the actually cos mu equal to 1 minus 2 omega Ls, this is basically the line to line voltage into ID, where line to line voltage equal to root 3 V max from there we can see that this part is basically the DC output voltage without the source inductance, and due to the source inductance this part will added up and that will reduce from the DC bus voltage. So, this is the effect of the source inductance diode rectifier feeding RL load. Now, same way we can draw the same kind of thing for the thyristors for the full control converter, so having a source inductance. So, ultimately this is your source voltage and this is your input current, and since this is the transition takes place, ultimately you will find that actually current will actually ramp on in this shape due to the source inductance, and since this area here you will find that output voltage, you will find it is jagged. It is basically the conduction of the both the thyristors for some interval of time. So, mu is the area where actually you can see that T3 actually is going on and T4 is going on. So, for this reason this overlap regions come, and this is the voltage blocking capability of the thyristor till Vt1 actually at an alpha it will block. So, ultimately this voltage will be 0, but unfortunately in this region mu both those actually thyristors are conducting, and similarly in this region also both the thyristors were conducting. So, we can write for the single phase LDIdt equal to V1, and again for I1 we have chosen that actually constant load current. So, actually it should be equal to I0. So, we can find out actually input current I1 equal to I minus under root Vi cos omega t. From there actually we can find it out the input current will have this fashion. At omega t equal to alpha plus mu, this value you can refer back to this figure, this value is basically I0. So, this is the average load current flowing across this actually the load, and we assume that actually constant load current. So, for this reason and alpha equal to mu, so input current becomes I1, input current becomes I0, and thus we can substitute from there, we can get the equations cos alpha minus cos alpha plus mu, basically this term. From there we can find it out that output voltage, which is supposed to be root 2 Vi or Vm by pi cos alpha, then it will change to cos alpha plus mu, and thus we can rewrite these equations. We can write it in terms of load current, which is assumed to be constant, that is root 2 by pi Vi cos alpha minus 2 by pi omega L into I0. So, voltage will drop according to the value of the I0. More the value of I0, you will find more the drop in the voltage. So, similarly this whatever we have discussed in case of the diode based rectifier, it can be extended to the same concept to the actually full control converter. Here in this case, for it is triggered at an angle alpha. So, you can see that actually this changeover takes place. So, T1 was conducting, and here in the region actually there is a changeover takes place between 2 and 6. So, basically 6 was conducting, now since actually 2 becomes more negative phase and it will be get into the system, and since you will find that actually that current decaying through the T6 and current build up in T2 will take a time mu, and similarly same thing will happen in this duration when 1 and 3 will interchange, and thus you will have a drop in the voltage that in been shown with the without the source inductance you should have get this, but you will get this much of less voltage due to the source inductance. Ultimately you get the load voltage as the unshaded part, that is a white part. Total voltage would have been basically the shaded part. So, huge, you can see that there will be a huge drop in case of the thyristor, because turn on you can control. This is a case almost it is alpha is less than 60 degree. So, we can write the equation here also, that is omega t should be greater than alpha and you are t at an angle alpha to mu. So, you write it down the equation the phase B. So, similarly phase BC will be actually the current between IB minus IC into del di dt. Since it is 3 phase 3 wire system, so this equation will hold good. So, for this reason actually you can substitute dIB by dt equal to minus this, and you have assumed also a constant load current, thus differentiation leads to 0. And so, from this equation we get 2L di dt B equal to voltage BC equal to under root VL. Similarly, you can substitute these values and ultimately you get for alpha plus mu for IB equal to 0, where under root VL to omega L cos alpha minus cos alpha plus mu equal to I0. And thus, for mu less than equal to 60 degree, so I0 should be less than equal to VL by under root 2 omega L cos alpha minus pi by 3. These equations will hold, and for the continuous conduction mode we have to have this condition to satisfy it, so that this will get our continuous conduction mode operation. So, what should be the expression of the voltage in this case? So, we shall write it down the voltage. Output voltage should be equal to 1 by pi, since there are 3 such cycles, it will multiply by 3. So, and it is a region basically alpha to alpha plus mu Va d omega d alpha plus mu to alpha plus pi by 3, you will get a voltage of the line voltage AC. So, you just expand it and ultimately you get 3 root 2 by pi VL cos alpha minus 3 by 2 pi alpha to alpha plus mu VDC. From there you can calculate, this value is 3 root 2 by pi VL cos alpha minus 3 by pi omega L I0. So, if you can compare the results of the diode-based rectifier, so it is almost same. So, this is the value actually for the diode-based rectifier. So, it is 3 by pi line to line voltage 1 minus omega Ls IT by VL, and here you are getting essentially the 3 root 2 by pi VL cos alpha minus 3 by pi omega L into I0. So, cos alpha term will come because you have a choice of triggering in case of the full control converter. So, now let us conclude that effect of the source inductance all the type of actually the converter as well as the rectifier. Generally what happened due to the effect of this actually due to the effect of this source inductance, THT generally improves, but you get lower DC voltage and lower power factor. So, this is the actually problem of the source inductance, and sometime you may have a commutation failure if source inductance was quite high, because you may have a both the thyristors were conducting in a same leg, and that may lead to a line shorting condition. Now, let us come to the little bit new topic, that is pulse width modulation rectifier. So, now actually we have seen, we have a conventional AC to DC converter has few demerits. Demerits are the power qualities, and then for the high power applications we may go for basically difference instead of the 6 pulse in 3 phase, we can go for the multi-pulse operations, and we can see that considerably the power factor will improve, THD will improve. but that require a complex transformer and things are bulky and costly. So, why can't we wish to have a improved power factor without those hassles? That was the basic motivation to do that. And another aspect is that that is feasible also for the very high power application. For nowadays actually, due to the penetrations of the electronic gadgets, mostly SMPS, laptops and other mobiles. So, we have huge requirement of the small power DC charging, DC power. So, in that case also we require an entity which actually improve the power quality issues, and it is not feasible to put zigzag transformer for household applications. And for this reason a new actually topic has popped in power electronics, and that is pulse width modulator rectifier. So, what are the desire? It is desired that the rectifier presents a resistive load to the AC system, and we require basically unity power factor and AC line current as same wave shape as actually IAC equal to VAC into RE, and RE is called the emulated resistance. So, we shall see that as if that a resistive load is connected, so there is no power quality issues. Unfortunately, what happened? We have a nonlinear transformation, thus we inject harmonics, and average power basically V square by RE, the apparently consumed by RE is the actually transmitted to the rectifier DC output port to control the amount of the output power, and it must be possible to adjust the value of RE. So, we can control the value of RE to way to control the output dispatch into the system, like you are charging a mobile. So, there is a different kind of charging method. First you go for basically the first charging, because when you are, and so it will consume actually more power. So, for this is RE required to be changed. Then you may actually charge as a constant current mode. Thereafter, you know, actually when you have actually increased the actually SOC or the battery charging around 80%, then you may actually go for the boost charging. Thereafter, once it is fully charged, but it will be discharged slowly, so you keep it in the trickle charging mode. So, in those 4 mode actually you require a different kind of power to be supplied to the load for the modern power electronics gadgets, and thus the value of RE required to be changed accordingly. So, the ideal rectifier, we shall define what is ideal rectifier, it never happens, but we can aspire to get those things. The ideal, so this is the output model, something like you have studied in equivalent model of the transformer. So, this is the output model. The ideal rectifier is lossless and contains no internal energy storage. Hence, the instantaneous power equals the instantaneous output power. So, whatever power has been consumed, it is just like a transformer. Unfortunately, we require power electronics, it is because of that we cannot have a transformer operation in DC. So, DC transformer operation require the help of the power electronics. Hence, the instantaneous power is independent of the DC load, and DC load characteristics, the output would obey the power source characteristics. So, this is basically the input voltage AC, it may be regulated or unregulated, and this is a current through it, and you have a control resistance that will change according to the power you are trying to submit into it. So, ultimately power will be AC square RE, and so you will get a DC output voltage as desired by the consumer. But the AC side will see as if a resistance is connected to a system. Like you are switching on one fan, some power is consumed, but also that is also wrong, because fans also comes with the inductance, and let us say resistive heating you switch on another resistive heating. So, accordingly basically the RE changes, something like that. So, you have to aspire to get that kind of features while conversion of AC to DC. So, power consumed is essentially V square by RE, and where we have a control over the RE, and ultimately it is Vi into Ti equal to Pt Vc square RE. Now, define the equations of the ideal rectifier. Ideal rectifier will assume that as if a resistive load is connected, power factor is unity, THD is 0. So, what happen here? So, AC by RE control, so that will be the actual current flowing through the AC part of the circuit. No actually trapezoidal, no square wave kind, it will be a pure sinusoidal, that is what we aspire to have. And thereafter the power, it is simply the multiplications of V and I, thus you got a real power without any imaginary, all the ripple component comes from the harmonics. So, thus we defined the power V square AC, that is basically it is RE is a voltage controlled. And when connect to a resistive load of value R, the input and the output voltage of the current is related as follows: Vrms by SCRMS equal to under root by R by RE, and similarly it is actually SCRMS by IRMS is R by RE. So, it is something it is just looks like a something like transformer. So, how you can achieve it? We can achieve, and we please understand that these are mostly applicable for the at present household application due to high penetration of the laptop, desktop and mobiles. And so, power rating of this actually device is quite low. But if you have a 4 laptop in your house and 4 mobile, so that also create a huge distortion into the system. The control duty cycle of a DC to DC converter such that input current is proportional to the input voltage. So, here essentially you can't do much, you have to have a rectification here, and it is simple actually the diode based rectifications, and thereafter you get a DC voltage. You take an example of actually your mobile charger or laptop charger. Generally laptop charger will have a voltage of 18 volt, 18 to 24 volt depending on the power rating of the different kind of system. So, generally, so if you rectify it, since load is quite low, so you get around this voltage is around 310 volt. So, that is almost a peak value, it is not actually 2 Vm by pi, that is average value. So, here actually you have a control and power will flow from it, and the duty ratio instead of 1:n, that will be actually multiplied by the modulation index of this actually the switching of the converter, and you will be actually stepping down maybe 1:n. Thereafter you will continue to do that and you will may get actually 18 volt DC here. This is the whole purpose of actually a simple DC to DC converter. Let us see what is actually its methodology involved to design these circuits or the principle of operation. So, we have Vm that is varying, and please note that different voltages here, since it does not have any capacitor. So, this point voltage will change according to the input voltage. So, you have a just double frequency ripples, that Vg will be a 100 Hz ripple DC, not that a constant DC. So, But if you do that, then actually you distort the power factor. For this we do not do that. So, you have PSE that will be actually that required to be basically a sinusoidal one, but you know that how the voltage looks like in case of the actually a diode based rectifier, input of the diode based rectifier. So, instead of this kind of thing, we want that this should be pure sinusoidal. For this is what we require to do, since we have no capacitor. If you put a capacitor, then current will be actually peaky and actually corrupted with the lot of harmonics. So, Vg is this, since you have not put any capacitor, and Ig should be the same thing, because you know you have assumed that basically it is just divided by R, just it is a amount of the scaling. But in output you want a constant DC voltage, let us say 18 volt or whatever maybe. So, we require to change the modulation index. It is something like your trans ratio itself is modulating, because you have a variable turns transformer maybe. So, your accordingly basically, since voltage is varying like this and your trans ratio required to be varying like this, then only you can actually get this kind of constant DC voltage. So, what is the advantage of it? Advantage of it that you do not have a problem of all the nasty power quality issues that comes into the picture due to the AC to DC conversion. So, can we have it? That is a challenge. So, let us define some parameters, F expressions, and we will continue our discussions also in next class. So, average, so it will be the value of I t is given by actually Vgt into Ig by V, that is basically we can write it like V square G V into Re, and for the period It you can write V square m by V Re sin square omega t, and thus since it is rectified we have a double frequency oscillations, and thus we will find that current will have a double frequency ripple, that is V square by m to V Re. This part is essentially DC, but you have 2 omega t with cos, that will be giving you the double frequency ripple, and average over the AC line period will be basically ITTL. So, it is V square m by 2 V Re. So, this will be the power, that is V square by V square m, that is the peak value of it, by 2 Re. So, this is the expressions of the output side current, and this is the expression of the average AC input side current. So, this is the overall topology and the realizations of the near ideal PWM rectifier. Now, we shall continue our discussions in our next class with the PWM different kind of PWM different kind of rectifier, PWM rectifier, and its application, how we can achieve this actually desired feature by this technique. So, of course, you will have a lot of merits to use it, and beauty of it, it is a high frequency transformer, since actually it is very high frequency. Generally, you know, actually expression of the voltage of the frequency, if you assume to be this part is sinusoidal, it is BANF. So, you know, if you increase the value of f quite high, that frequency, then this part essentially that this is a actually geometry of the core. B is the flux density and the area is the core. So, B depends on the material, that kind of material we will choose, and A is the area of the cross section of the core, and that is what happen if you keep the V value ferrite or anything, that depends on the matter of choice and the cost, and you can reduce the value of A by increasing the value of the frequency. So, and thus we can see a very compact actually transformer which can be modulated by the power electronic switching. Thanks for your attention. I will continue to our discussion in next class with the PWM rectifier. Thank you.